Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to help out with your homework on right-hand rule and magnetism. So we're going to look at problems number 1 and 6 here on the Unit 5 homework entitled Magnetism, AC Circuits, and Induction. And these problems are talking about various situations at the equator. Now I'm going to talk about why the word equator here is fairly important. If you've seen my videos about the Earth's magnetic field, I'm going to do a quick sketch here. The Earth's magnetic field is basically has the shape of a giant bar magnet. So if I were to draw some field lines around the bar magnet, and again, it's not that there's a giant bar magnet in the Earth, but the field shape that you get is what's called a dipole field, which is the field lines that look like it came from a bar magnet. And one of the things you notice is if I look at, if you're somewhere in the northern hemisphere, you'll notice that the magnetic field lines point into the Earth at a certain angle. And then in the southern hemisphere, they also have an angle with respect to the ground. But if you happen to be at the equator, that's the location at the Earth where the magnetic field lines, if I draw one right through here, is tangent to the ground. So it makes it a relatively simple place to talk about these examples. All right, so that's why we're even talking about the equator. Now, what I've done here is I've drawn a little kind of coordinate system here, and I put a couple references in here so that we hopefully understand what these directions mean. So in this example, imagine this young biker is biking due north, right? So to the right is going to be due north. East would be the direction that this astronaut is then facing. And that's what this represents. Now remember, I'm trying to draw a three-dimensional coordinate system on a two-dimensional page. So I know it looks a little funny, like, why does this kind of look like this? Well, this is how you draw vectors that look like this. This would be basically a coordinate system that's pointing at you, just like this fella. All right, and then dead away would be, or I'm sorry, west would be if the astronaut reversed direction. South would be this way. Up is just as shown, and then straight down. So what I do is I just want to go through some examples here that are like problems 1 and 6 in your homework of determining magnetic forces. So let's imagine that we've got a positively charged particle and it's fired due east. So the velocity vector then would point this way, parallel to this. Now it's important to realize what that means. Basically, it's pointing in the direction that this astronaut is pointing, right at you. So imagine this proton basically is coming right out of the page. The magnetic field points due north. And what we have to do now is we have to apply the right-hand rule to this. Now this is kind of tough to do on a two-dimensional page. I made other videos that were that were recording me demonstrating the right-hand rule. So if you don't know what I'm talking about when I go over this example, you're going to have to review those videos on that. If you put your fingers parallel to V and sweep towards B, your thumb should be pointing up. So the magnetic force on that particle would be up. So again, if we have a positive charge fired east, the force on it should be up. I'll go through another example. All right, so let's imagine that we have a positively charged particle fired, up. So in this picture, the velocity vector would be this way. And again, that's an example, this vector represents the speed and direction that this particle is moving in. This arrow over it means that it's a vector quantity. The magnetic field at this location still points north. Remember that the magnetic field is defined as the direction that a compass points. All right, so this arrow is basically giving the direction that a compass would point, which would be due north at the equator. So now to figure out the force direction, put your hand parallel to V. If you're watching this video, put your fingers parallel to V. Rotate your hand so that you can sweep towards B. Your thumb should be pointing directly into the computer screen, which in this example means opposite of this, means west. So in this example here, if the velocity is up, then the magnetic force ends up west on a positively charged particle. So these are examples of how to do number 1 and 6 in your book, and I'm going to try to keep these relatively simple here. I think I'll do one more, and I'll talk about a negatively charged particle. Clear this. All right, so now imagine we have a This is a plus. A negatively charged particle with a velocity that's east. Actually, we'll do west. So here's a minus. Now the way we would draw a velocity vector west is I'm going to draw it parallel to this. Or a lot of times in the book we would draw it like this, either one. This represents a vector going away from you. In fact, I think for this example that's what I'll do. So the velocity is west. And again, that's the way you draw a vector going away. Magnetic field is still to the right. Now, there's a couple ways to handle this when you're talking about negative charges. You can either do right-hand rule, same as always, and just reverse the direction because it's negatively charged. That's what I like to do. Or you can use your left hand. Left hand will correctly give the force direction for a negatively charged particle. I'm going to go ahead and just use my right hand. So if you're watching this video, put your right hand, it should be pointed right into the screen. Rotate so that you can sweep towards B, so you're sweeping towards this vector right here. Your thumb should be pointing down. So if this were positively charged, the force direction would be down. This is negatively charged, so the force direction is up. All right. So there's some examples similar to 1 through 6 in your homework. I hope this video helps get them correct. It's important to understand the right-hand rule because it's absolutely fundamental for understanding how magnetic fields affect charged particles. All right, hope this video helps. Have a great day. Whoops.